So hello everyone. Today I'm going to introduce our research project, a robust conformal uncertainty handling framework for safe cloud navigation. And I am Jianpeng. So let's first view a typical dense intersection, and we can see that the human dynamics are quite complex. And in this scenario, we cannot predict the human positions very perfectly. While in the same time, prediction-informed decision-making has been widely adopted in trajectory planning, whether it's mobile robots or autonomous driving. And this insight can apply to a wide range of applications, algorithms, like including the learning rule and optimization-based algorithms. However, we think that in these current solutions, we observe a dual path overfitting, and especially for reinforcement learning agents. And the first overfitting path is the data prediction. If we train a prediction model from unlimited data, we may acquire a model that is very good for this data distributions, while it may not be well applied to other scenarios. And another path is the simulation, is the environment dynamics overfitting. Like we have an agent trained in a simulation environment, and it may overadapt to this environment and may not perform better when OOD scenarios. So in our paper, we think that uncertainty can serve as an indicator for distribution shifts. And the first very obvious distribution shift that it can represent is the prediction uncertainty, since the prediction uncertainty can be naturally calculated by using the prediction and the ground truth positions. And if we take a step further, we think that prediction reflect the expected dynamics, and the ground truth positions reflect the ground truth dynamics. So we think prediction uncertainty can also reflect the distribution shift in the underlying dynamics. And because these two dynamics are the upstream of both predictions and ground truth positions. So our methods introduce a framework for quantifying uncertainty and then subsequently using it to inform and guide the learning process of agents. So for the first key part, I think that we quantify prediction uncertainty using adaptive conformal inference and concatenate it with the other features to input it into the agent. This is how we quantify and inform the agents. And the second part is the constrained reinforcement learning. We use constrained reinforcement learning to integrate extra controllability compared to regular reinforcement learning agents. So the first part, we use we quantify prediction uncertainty as a key measure for distribution shift. And the first thing we do is to compute the prediction errors based on the model-generated prediction and the ground truth positions of humans. And the second thing is that we have multiple estimators, and they will adaptively adjust based on the performance with different learning rates. And the second thing is that we evaluate the performance based on their past performance, and then we adjust the weights of different estimators. And the last thing is we just sample and error estimates. So for the second key part of our paper, we use the constraint reinforcement learning so that we can enhance controllability and use it to more effectively manage uncertainty-driven behaviors. So the first thing is that how we formulate our cost. We use the maximum intrusions into the uncertainty areas around humans, and we think that using this behavior level cost, we can the constraint reinforcement learning agent can receive dense feedback, and this is very effective for policy guidance. So the second thing is the constraint reinforcement learning implementation. Using constraint reinforcement learning, we can constrain the expected cumulative intrusions into the uncertainty areas, and we can provide the continuous guidance for safer reactions to distribution shifts. So here's one of the results. Like we trained these are the training curves of using reinforcement learning versus the constraint reinforcement learning. We can see that the pink curve. We can see that when we use constraint reinforcement learning, the training curves converge faster with higher rewards, and the And the second thing that I think is very interesting is the adjustable cost limit. In this way, we can see that when we change the adjustable cost limits to different levels, the mean cost converge to different levels. And in this way, we can tune the aggressiveness and robustness of agents to distribution shifts. So about the quantitative analysis, we have done a lot of, and we show some here. We can see from the results that our approach outperforms other SOTA by over 8.8% in success rate, with over 3 times fewer collision rates in distribution scenarios. And unlike other reinforcement learning algorithms like SafePron, although it performs well in distribution scenarios, but performs worse in other scenarios, our methods exhibit stronger robustness across all OOD scenarios. Yeah, and here's a comparison of our methods versus the baseline. And we can see that our model shows stable yielding behaviors, and this can help generate safe and robust trajectories. So here are 3 OOD visualizations. We can see from the results that our methods show robustness to velocity variations and policy changes and group dynamics. So we also include some real-world experiments in our paper, and we can see from the video that the robot behaves quite robustly even when the humans are running towards it. So to summarize, we present a robust uncertainty-aware framework, and we introduce a behavior-level constraint mechanism into the framework. And the second thing is that our method achieves the best performance in distribution and all OOD settings. Thank you.